dear students, welcome back to the tetrahedron chemistry classes. So in the combined spectral problem, today I am going to discuss another problem, which is my problem number 11. And you have been given this particular compound. Say the molecular formula of the compound is C6H8O2, right? If you are not able to see exactly the formula in your mobile screen, so I can little bit zoom this. Okay, now it is quite clear. The molecular formula is given C6H8O2, and along with this C6H8O2 you have been given these four spectra, right? One spectrum is IR spectrum, second one is the mass spectrum, third is the carbon spectrum, in which your depth NMR segment is given, and this is your 13C NMR, and at the last there is proton NMR spectrum. And with the help of these four spectra, we have to identify the most probable structure for this particular molecular formula C6H8O2, right? Now you can understand in that manner. Some of you, if you are regularly following my lecture on spectroscopy, or you are in continuous touch with this spectroscopic techniques, then this is the very simple problem for them, right? But for beginners, this problem seems little bit tricky, but believe me, this problem is not that tricky. It's a very simple problem, but the only thing is that how we can approach such types of the questions. So I'll use the same methodology which I generally used in my earlier lectures as well. Okay, so first of all, you have been given the molecular formula, and that molecular formula is C6H8O2. So my routine work in solving this particular problem, right? The first step is what? Calculation of index of hydrogen deficiency or hydrogen deficiency index, which is your HDI. Okay, and the formula of the HDI is 2 times N plus 2 minus M times of H divided by 2. This is the formula, right? And where this N is the number of the carbon atoms. Please remember, N is the number of the carbon atoms, which are 6 in that case, and M is the number of the hydrogen atom, which is 8 in that case. And with the help of this, you can calculate hydrogen deficiency index. That would come 2 times 6 plus 2 minus 8 of your hydrogen divided by 2. Okay, it simply means 14 minus 8 over 2, that is 6 by 2, and 6 by 2 is 3, right? So what is the use of this hydrogen deficiency index? The use of the hydrogen deficiency index is that whenever you have this value, this numeric value for HDI, say it is 3 now. So what is the meaning of this 3? Your molecular structure, in that case, there are number of possibilities. First possibility is that 3 rings may be possible in your compounds. This is the first possibility. Second possibility, 3 double bonds may be present in your compound. 3 double bonds, right? Third possibility is 2 rings plus 1 double bond may present in your compound. Fourth possibility, 1 ring plus 2 of the double bonds may present in your compound. There may be other possibilities also. You can check by your own. Now you can see here, if you clearly see this molecular formula C6H8, it is generally, up to now, you may think that okay, it is looking like a benzene. Okay, when you consider, I'm not saying that it is benzene, but beginner may think that C6H8 is the perfect number for benzene. Okay, so when one benzene is present, that means your compound cannot have 3 rings, so you can safely discard this first possibility. And if you are considering the benzene, that means 3 double bonds may present in that case, so this possibility may exist, right? But third one you can discard very beautifully again, because 2 rings are not possible. Okay, and if you consider benzene, then 1 ring plus 2 double bonds, this is not possible at all, because benzene must have 3 double bonds inside it. Okay, so only the two possibilities which are looking good, that is option number 2, 3 double bonds. Okay, and say up to now this only this much information you may have. Okay, so now what we can do after that, we can analyze the IR spectrum. Actually, what is given in the IR spectrum. Okay, now see, since this is where oxygen is also present, so you may think that your compound may be alcohol type of compound, your compound may be acid type of compound, and this may be your ester type of compound or anhydride type of compound. These possibilities can exist. But some of you may also think, no, ketones may also be there. Okay, and along with the ketones, aldehyde is another possibility. Oh, these things can be present in your final structure. So what you will do, you will first we will analyze the IR spectrum, and now I am zooming my IR spectrum. Right, this is my IR spectrum. Now I think it is quite clear to you. You can see here, nothing is present here. This is the region of the OH group, whether this OH belongs to the alcohol, phenol, acids, anything. See, nothing is there. When this OH group is not present in the IR spectrum, it is quite clear that your compound is not alcohol, it is not your acid as well. So these two possibilities you can safely discard. Now what you left with? You left with ketone, definitely, and then you left with your aldehyde. This is another possibility, and then you left with the ester as well, or anhydride as well. These possibilities may exist. Now if you again clearly analyze that, you think you see here what is given at 1693. If I again little bit zoom this, you can see here at 1693, okay, very sharp band is given here. It is very sharp and it is very strong band. When sharp and strong band is present, this shows the presence of the carbonyl compound. So basically, if you see, this is due to the presence of the carbonyl functionality. But again, question remains the same. If it is the carbonyl functionality, then definitely your ketone, aldehyde, ester or anhydride, any derivative may present. Now if you see here, the value of this 1693. See, if you know, if you have learned the ranges of the carbonyl groups, then it is quite easy for you to tell that this 1693 basically belongs to the ketone, right? Please remember one very, very important point. If you are not very much aware about the stretching frequencies of the carbonyl group, for ketone it goes from somewhere 1700 to 1720 centimeter inverse. Please remember, okay? For ester, this value is quite high, somewhere around 750 centimeter inverse. That means you can discard this ester, okay? And if you see the aldehyde, right? If you see the aldehyde, for aldehyde as well, this value is somewhere between 1720 to 1750 centimeter inverse. So you can discard this aldehyde as well, right? On the same ground, you can also discard this anhydride. So your most probable compound actually will have this particular functional group CH2. So now from here, two things are quite clear. What are the two things? So let me erase some part of this. So what you have concluded up to now? You have concluded that presence of the carbonyl group and presence of one ring. Because see, benzene, why benzene cannot be the answer? Because one double bond is there. That means you cannot consider a triple bond present in the benzene ring. That means one ring is present. And that ring, because 6 carbons are there, that ring must be cyclohexane. That means you are having these two things. First is having this one and second one is having this one, right? And when you are having this cyclohexane ring, that means here CH2 is present. So 6 carbon and 12 hydrogens. And if you see, molecular formula is exactly like that, C6 and H8. These four hydrogens we can adjust at the end, right? Up to now you are having, say, these two possibilities, one 6-membered ring and one carbonyl frequency. Only this thing you are having. Now you can see here, this is very, very important point, guys. This is basically your methyl or methylene stretch. So I am writing here, this is methylene stretch. This is the region of the methyl and methylene stretch. But since we are considering the 6-membered ring, so where we can say that it is basically this is a CH2 stretching. But if you know the IR nature of the IR spectrum, then you can very quickly say why this band is very, very weak, right? So please remember one thing, it is the key for you, right? Whenever you have very, very symmetrical structure, please remember, whenever you have very, very symmetrical structure, and then your intensity of band will be low. See, symmetry generally brings down the number of the bands and number of bands in the IR spectrum, right? And number of you can say the peaks in the proton NMR spectrum and lots of things. Symmetry brings these things down actually. Okay. Now, see, you may wonder that why actually it happens that when you have very symmetrical structure, then the intensity of these bands goes low. Of course, in this simple 2D drawing, it is quite symmetrical. So due to this symmetry, basically there occurs the reduction in the dipole moment, and when the dipole moment reduces, right, this actually weakens the absorption band. This is the first region. Second thing is the ring constraint is also there. See, the cyclic structure, especially in the alicyclic compounds, they restrict the free movement of these CH2 groups, and this constraint reduces the amplitude of the stretching vibrations, which further decreases the intensity of the band. Similarly, these vibrations may couple with the other vibrations as well, and these this coupling is also responsible for the weakening of this band, right? Basically, polarizability is quite low when your structure is quite symmetrical, especially in the cyclic compounds, right? That's why it is quite low. Now it is quite clear from this IR spectrum, 6-membered ring is quite probable in that case. These things you must remember. Okay, so from IR spectrum we can get this much of information only. Now let us move to other spectrum. Right now I am not focusing on the mass spectrum, but I will focus on the carbon NMR spectrum. You see here, this is my carbon NMR spectrum, and here you can see this is Dept NMR is given, and another very important and valuable information you will get from this Dept NMR spectrum. You see, this is negative peak, right? Peak which shows in the downward direction. It is the negative peak, and this negative peak basically shows the presence of the methylene CH2. If the peaks are on the positive side, then methyl CH3 and methine CH are there, and you know there is no peak in this positive region. That means CH3 and CH cannot be present in your compound, but this inverted or the negative side peak, it shows the presence of the CH2 group. And key is here again, if I little bit zoom this particular spectrum, then you can see here CH2 is downward like that, and CH3 and CH up, but they are not present. That means your final compound is having only CH2. Again, it confirms that this ring is present in the compound. Very, very important. Now if you analyze your say this proton decoupled carbon spectrum, so in that carbon spectrum, this is the peak of the solvent. We have nothing to do with this one, and one, you see this peak is present here for carbon, which is somewhere around 35 ppm, right? And when it is at 35 ppm, it clearly shows that some some electron withdrawing groups are present in the vicinity of the carbon, and of course your carbonyl group is the electron withdrawing group, right? So this again confirms that ketone type of the compound we present in the compound. This is the one peak, and this is the very important one, the peak at 210 ppm. This is at 210 ppm. I am writing here, this is at 210 ppm, which is a very important characteristic of the carbonyl compound. So here again you can see we are confirming the presence of the carbonyl compound from this proton decoupled carbon spectrum, and presence of the CH2 at near about 40 ppm, right? And only CH2 is present here. So now what we are having actually, so one thing is quite sure, my compound is having what? The substitution of the carbonyl group. So I can substitute the carbonyl group over there like that, and second carbonyl group I can put here, because two oxygens are present, right? If you see the formula is C6H8O2, that means two carbonyls are present. Okay, now if you count the total number of carbon, hydrogen and oxygen is in this particular compound, then you will find 6 carbons are there, and 2 to 4 to 6 to 8 hydrogens are present here. So you can write 8 hydrogens here, H, 8 and 2 of the oxygen. So this is the possibility, but you may again think that this is not the only possibility. Your compound may look like this type as well, right? Second possibility. And the third possibility is this one, that means substitution at 1,4 positions. So your compound your compound actually could be anyone out of these three, out of these three. Okay, now say these are the 3 compound. Okay, now let us check the proton NMR spectrum. Now what is given in the proton NMR spectrum here? Again, a very valuable information you are getting from the proton NMR spectrum. You are getting the only one peak at somewhere around 2.8 ppm, somewhere, not exactly, but somewhere around 2.8 ppm, and it is a singlet. That means no splitting is taking place, only one singlet is there. That means no splitting is or no coupling is taking place in that case. If you consider this particular structure, then you have this CH2, right? This CH2 and this CH2 and this CH2 and this CH2, right? So these two are near to the carbonyl group. Definitely their chemical shift would be different compared to these two. That means these two hydrogen will couple, and these two hydrogen can also couple. Long range coupling may also occur. This will give you the splitting pattern. But splitting is not taking place. That means this is not the most probable compound. Now if you see the second one, this is CH2 here, this is another CH2, this is another CH2, and this is another CH2 here. Okay, now again you can see this CH2 group is flanked in between the two carbonyl groups. That means it must be quite downfield, somewhere around 4 ppm, but here you are getting the peak at 2.8 ppm. So this much of downfield shift, this much of downfield shift can be possible only when this CH2 is flanked between the two carbonyl group. Or moreover, when you consider this structure as the correct structure, so one peak for these two hydrogens and one peak for this one, right? That means 2 peaks must be there, but here only one peak is there. That means your second possibility also you can very beautifully discard. Now you left with the third possibility. Now you see this compound is having various planes of symmetry. So I am drawing different planes of symmetry here, guys. You see, right? This is one plane of symmetry. When I put this one plane of symmetry, that means this part and this part are identical. That means this is the symmetrical structure. Okay, and next symmetry I can put, symmetry plane I can put from here to here. So that means these two and these two, they are equivalent. Okay, so this is basically is the most probable structure because this is quite symmetrical one, and this symmetry is actually bringing down the number of the signals. This is the most probable structure for this one, right? So we can conclude that this is the most probable structure, right, which correspond to the given spectra, right? So I hope this is quite clear why we can how we can select this as the correct structure. But initially I left this mass spectrum actually, so let us take this mass spectrum as well. What it is saying that, see, 2 of the lone pair over here, 2 of the lone pair here, and when you knocked out 1 electron in the ionization, so this is basically your molecular ion peak. This is your molecular ion peak, and it corresponds to the 112. How 112? C6, that means 72. H8, very fine, this is 8. And 1 oxygen, that is 16. Okay. Then what will happen? Let's check. No, sorry, 2 of the oxygen, that is 32, not 1, 32. And this will give you 2 and 12, 112. This is the first peak which is present here, molecular ion peak. Second important peak is at 56 ppm. Now it's quite clear from here. If I break this particular bond from here, so this removal will give you this fragment, that is CH2, again CH2 here, and this is positive and dot, and 1 radical will lost from here. So if you check the molecular weight of this one, so 3 carbons are there, 3 carbons, that mean 36. 4 hydrogens are there, that mean only 4 unit. 1 oxygen is there, okay, that means 16, that means 6 and 5. M by Z 56. It is what? M by Z 56. So this M by Z 56 is here actually. So it is quite see, however, you can very easily conclude your answer as your this particular given structure only by considering the molecular formula and the proton NMR spectrum. But since we have been given these 4 different kinds of the spectra, so we have to use the information from all these spectra to get the correct picture. This is how we can solve such type of the problems. I hope this makes sense and you understood the reaction or you understood the concept well. If you like the video, then please give the thumbs up to my video, and if you are watching video for the first time, please subscribe the Tetrahedron Chemistry classes and do share with your friends as well. That's it for today. Thank you very much.